Good morning. Up until now, we've looked at derivatives of functions. These functions have an input of an x value and an explicit y value that pops out. Well, that's not always the case. So for example, let's say you had a circle or an ellipse. In that case, you wouldn't be able to find the derivative at a point because those guys aren't functions. But there's still an implicit relationship between them. There's an equation that ties all the points together. So how do we handle derivatives? Well, let's take a look at an example where we're studying a circle. So if I sketch this guy, centered at 0, it's got a radius of 5. And let's say I want to find the derivative at 3, 4. So 3 squared plus 4 squared is 25, so that guy lives on the circle. So how do we do it? Well, one thing you could do is realize that this circle is actually equal to 2 semicircles, and each of these guys is a function. So this is a little bit of an abuse of notation, but hopefully you understand what I'm saying. If I glue these two guys together with my plus, then I'll get the circle in question. In fact, we can figure out the top and the bottom. So, for example, this tells me that y squared is 25 minus x squared. So that y is plus or minus the square root of 25 minus x squared. So that means that this top function is the square root of 25 minus x squared. All those guys are non-negative. That's why it's the positive square root. And then on the bottom we have negative the square root of 25 minus x squared. So what I could do then is, if I want the derivative of 3, 4, I could say, oh, I'm living in this world. So let me say that f of x is equal to 25 minus x squared to the 1/2. Thinking ahead that I'm going to take derivative using the power rule and the chain rule. Then I could take this derivative, 1/2 times 25 minus x squared to the minus 1/2 times minus 2x. Just the chain rule, and then I could just plug in my 3. So we get 1/2, 25 minus 3 squared to the minus 1/2 times minus 2 times 3. And let me actually work this out. 25 minus 9 is 16. The square root of 16 is 4, and that'll be in the denominator. So we have 1 over 2 times 4 in the denominator. And we get minus 3 over 4. So this tangent line then has a slope of minus 3 over 4. So I don't know if that's a coincidence or not, but that's really interesting that I'm getting out the 3 and the 4 as part of the answer. So that is this guy's derivative. You could work out this derivative as well. So for example, 3, negative 4. And you then use this function. Well, this works fine with the circle because I know how to break it up into 2 pieces. But let's see if we can find a more general process that works so that I don't have to actually think so hard. Well, let's back up here a second. And let's realize that x squared plus y squared equals 25 can actually be thought of as x squared plus y of x squared is equal to 25. So what do I mean by that? Y of x is just some function. And in fact, this y of x is actually 2 different y of x's, depending on where, well, it's 1 y of x depending on where I am. But the possibilities are 25 minus x squared and minus the square root of 25 minus x squared. Either way, you could think of this as being a function of x. So if you take your x coordinate plus the square of your y value, where y is just some function of x, right? It was either this guy or this guy, then you'll get 25 back. Now, why does that help me? Because once I recognize that y of x is a function of x, again, it might be this, it might be this. I'm just representing it abstractly as y of x. Once I recognize that, I realize that this is something that I can actually differentiate, regardless of what the particular function is. How do I do that? I just use the chain rule. This becomes 2x plus 2 times y of x times the derivative of the inside. Now, again, I don't know what function it is, and at the moment, I don't really care. So this is just taking the derivative using the chain rule. At this point, I could leave this as y of x, but what I like to do, and I think all my students like to do this as well, what I like to do at this step is suppress the x. So again, y is some function of x, but it's just too many x's going on in that step. So I rewrite it as just y. And now let me solve for dy dx. So we get that dy dx. Let's see, I can bring the negative 2x over here. I could then divide by 2y. Beautiful. We get minus x over y is dy dx. Remember the minus 3/4? That's where it's coming from. So it's not a coincidence. In fact, this is telling me that on a circle, you have this interesting thing going on, which is that the derivative is just a ratio of the x and the y coordinates. In fact, let's just verify a couple of points. If we're here, we're at the point 0, 5, horizontal tangent of 0. Well, that is 0 divided by 5, 0. Over here, let's do another one. This one should have a derivative that doesn't exist. Let's see, this is negative 5, 0. Well, if we divide by 0, we'll get something that doesn't exist. So what we've just done here is called implicit differentiation. Again, the idea is that there's not an explicit relationship between x and y, but there is a relationship. And this is incredibly powerful, in my opinion, because we're abstracting away what the specific function is. We're just saying, hey, it's some function. And with that knowledge, we can then compute the derivative. Way easier than this, especially if you think about it, when we have more complicated equations that we're looking at. So as an example, let's say you had some equation, I don't know, maybe it's the path of a bumblebee or something, and this is what it looked like, and you're trying to find the derivative right here. So there is a function that exists. I can cut out this piece here. Actually, sorry, I can't even cut out that much. That wouldn't be quite a function, but I can cut out this guy here. Somehow, maybe, don't know, and then compute the derivative with respect to x. Maybe I could do it, or maybe it's actually not possible. It might be too complicated for me to play this game that I first played here, where I broke it into 2 pieces. But with this new process, this implicit differentiation, we don't have to do that. We're abstracting away what the function is. We're just saying, hey, yeah, there's some function there. And once we abstract it away, we can just use the chain rule. So let me give you an example like that. So let's say we have x cubed plus y cubed equals 6xy. So, yeah, I don't know what this looks like. That's first off. Second, I'm not even interested in the derivative at a point. I want the general derivative. So if I could break it into pieces, I'm sure it's going to be some sort of monstrosity. So let's use the process that we used before. So what was the process? The first thing that we did is we recognized that there's some y of x function lurking about there. And technically, you actually don't have to do this business of writing it as y of x, but from having taught this a lot, I can tell you that students who don't write this as y of x have a much higher chance of forgetting the dy dx piece which comes next. In other words, let's take the derivative, and by writing the y of x, I'm remembering that this is a function of x, so I need to multiply it by the derivative of the inside guy. Pause the video, see if you can come up with the derivative of 6x hint times y of x. Right, hopefully you gave that a shot. Product rule. First times the derivative of y of x. Well, again, I don't know what y of x is, but its derivative is notated by dy dx. First times the derivative of the second, plus second times the derivative of the first, which is just 6. So at this point, again, there are too many x's all over the place, so I will suppress the x. You get 3x squared plus 3y squared dy dx is equal to 6x dy dx plus 6y. And I'm just reordering the end. It's just customary to put numbers before letters. So now we need to solve for dy dx. Pause the video again and see if you can do that. All right, hopefully you gave that a shot. My strategy is going to be to put all of my dy dx stuff to the left and then factor out dy dx, put all of my non-dy dx stuff to the right. So let me bring this guy over here. Let me bring this guy over here. Okay, so let me factor out dy dx. So we have dy dx times 3y squared minus 6x is equal to 6y minus 3x squared. And then finally, I can divide both sides by 3y squared minus 6x. Very complicated derivative. And notice that this derivative depends on both x and y. And that makes sense to me because, thinking back to the circle example, depending what your x and y are, you can be on either one function or some other function. So in summary, in today's lecture, what we did is we looked at implicitly related functions or implicitly related variables where we have some sort of equation relating the two, but it's not a functional relationship. We then took advantage of the chain rule to actually come up with the derivative at a particular point, or dy dx. And we noticed that in this section, when we have this situation, the derivatives are going to depend both on x and y. That's all I have to say for today. Thanks for listening, and I'll see you next time.